Bum 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 bum.
And now we're going to look at the situation where we have n rectangles. So we're going to divide our region up into n rectangles and see if we can come up with a relationship here, a general formula, not necessarily something that we can solve, but something that will be useful nonetheless in helping us to move forward. Sometimes we have to do things that don't seem very helpful, but find that later on they end up giving us what we need. So we have some number of divisions in here. We're going to divide this up into n rectangles. Hopefully you see that that means that each rectangle has a width of b minus a over n. So the width of each rectangle will be b minus a over n. And we actually give this width a name that's going to maybe lead us to think about this in another particular way. We're going to call the width of our rectangle delta x. So the width of our rectangle here is b minus a over n. And then we have all of these points. Let's go ahead and for this particular example, let's take every left endpoint and estimate the areas based on the values of the left endpoint. That means that our first endpoint is f of a, and our next endpoint is f of a plus 1 delta x. Right? It's this point right here, that's our x value when we're over one of these delta x units. And then the next height will simply be f of a plus 2 delta x's, and so on and so forth until we end up with going all the way over, and we end up with f of a plus n minus 1 delta x's, and that would be the function value at the left corner of the last rectangle. And so what we need to do is we need to sum all of these up. To do that, we're going to use some summation notation. Right? So our area estimate is going to be the sum from, let's call it k, is equal to 1 all the way up to n. This is going to be the n rectangular areas that we're looking at here. And what we're going to have is we're going to have f of, we'll call it xk, so we'll have x1, x2, x3, x4, and we'll define those in a minute, multiplied by the width of our rectangle. So this is really the area formula here. We have the area formula for one rectangle. This is the height of our rectangle, and this is the width of our rectangle. This is what makes rectangles so easy and useful to work with, is that we have this simple area formula. We don't have to do anything super complicated here. But let's define what we mean by xk and what we mean by delta x. So delta x here, recall, is b minus a over n. It's the whole interval divided by the number of regions we're breaking this up into. And our xk, there are several ways we can define xk. I'm going to call this a, the left-hand side of our interval, plus k times delta x. So when k is 1, we're at the right-hand side of the first rectangle, so on and so forth. This definition, this collection of things together, gives us an area estimate. So the collection of things that we have together here gives us our estimate of our area. You can see here that we have a sum, and this is well defined. This particular object has a very important name in calculus. This is what is called a Riemann sum. This is a Riemann sum. We use it to estimate the sum of a finite number of rectangles in this particular case. And so if we choose our n high enough, we're going to have very, very many rectangles, and hopefully that will mean that our area estimate will become more and more accurate. the fact that it may not would have to do with the fact that there might be jumps in our graph or other places where things were not smooth. So let's go to the punchline here. Hopefully this is the thing that you've all been waiting for. What we're going to do is we're going to make our estimate as precise as possible. And that is going to involve us taking a limit. We have here our area formula is the sum from k equals 1 to n. We have n rectangles, and we're taking the area of each rectangle and working out what that is. What we want to do here to make this even more accurate is take the limit as n goes to infinity. Look at an infinite number of rectangles. And this turns out to be a very important and powerful notation, and we actually have a little way of writing this a little bit easier. We write this with this sign here that looks like an S that kind of goes along with sigma, a sum, and we're going to call this the integral from a to b of f of x dx. So here's our new calculus. Here's the new calculus that we're getting to understand here. It comes from the fact that we're really taking a limit. So again, limits are the key component in developing these techniques of calculus. We're letting the number of rectangles we look at go to infinity. And when you think about it, what that means is that our the width of each rectangle becomes closer and closer to 0, right? Remember that this is simply the width of our interval divided by n. Well, if n goes to infinity, the width of each rectangle goes to 0. We still have the function heights, but now because we have an infinite number of rectangles, even though the width of each rectangle goes to 0, something useful and interesting happens, just like with derivatives, where we let the 2 points get closer and closer together. Things get to 0, but the ratio actually stays the same. With integral calculus, we take a limit, and it turns out that the product stays constant. So it's a different way of looking at things. Right now, this is just formalism. This is just a way of talking about things in a way of sort of daydreaming. We haven't actually done any area problems with this method. We haven't actually looked at what it would take to find all of this material and how the limit would work. So even though we have sort of, in theory, come up with a neat way of thinking about this problem and solving it, we really haven't done anything with all of these pieces to understand how to make it work in a real problem. That's something that we will save for the next time, but for now we have developed a stepping stone towards this goal of being able to find the area under a curve.